This is a walkthrough of problem 3 on exam 2 from module 3, which can be found on page 70 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3 is a power supply is hooked up across two parallel thin conducting plates that are squares with 20 centimeter sides. The plates are 5 centimeters apart. The space between the plates is evacuated. A proton is released from rest at the positive plate, accelerates and reaches the negative plate in 0.1 microseconds. What is the voltage between the plates? What is the magnitude of the charge separated by the plates? Let's draw a better diagram than the one was given to us. We want to know the voltage between the plates. Let's put the proton in there. Bink, here's our proton. Proton's repelled by the positive plate, attracted by the negative plate. It's going to accelerate towards the negative plate when it's released from rest. We can calculate this acceleration. We know the distance, we know the time, we know the initial speed is 0. We convert everything to SI units. 5 millimeters is 0.005 meters. 0.1 microseconds is 0.1 times 10 to the minus 6 seconds. We solve for the acceleration, and it's 1 trillion meters per second squared. 10 to the 12th meters per second squared. From the acceleration, we can get the force, F equals ma. There's the mass of the proton, 1.67 times 10 to the minus 15th newtons. From the force, we can get the field, F is QE. Q is 1.6 times 10 to the minus 19th coulombs. The electronic charge, we can solve for E, 10,400 newtons every coulomb. And that's the same as 10,000 volts every meter. The field drops 10,400 volts every meter, but the plates are only 5 millimeters apart. The voltage is going to be much less than 10,400 because the plates are much less than 1 meter apart. 5 millimeters is a half a centimeter, which is 1/200th of a meter. So the voltage drop in 5 millimeters is 1/200th of the voltage drop in an entire meter, and we can calculate it. The change in voltage is the field times the distance, and we get 10,400 volts per meter times 0.005 meters, which is 52.2 volts. So we have the voltage difference between the plates. It's about 52 volts. Now we can tackle part B. Let's do part A again. Let's do it a different way. With the acceleration, we can get the final speed. V final is AT. It accelerates at 1 trillion meters per second squared for 0.1 microseconds. It's going 10 to the 5th meters per second, 100,000 meters per second. We know the mass, we know the speed, we can get the energy. 1/2 mv squared. 8.35 times 10 to the minus 18th joules. What is the voltage drop? What does it mean? The voltage drop means when I take a charged particle from here to here, the voltage is the energy per unit charge. I have the energy. I know what the charge is. Charge on a proton is the same as an electron, 1.6 times 10 to the minus 19th coulombs. So the joules per coulomb, which is the voltage, is just the energy divided by the charge. The energy is 8.35 times 10 to the minus 18th. You divide that by 1.6 times 10 to the minus 19th coulombs, and you get 52.2 joules per coulomb, which, as you know, is 52.2 volts, which is the same answer we got before. Now we can tackle part B. We're going to use Gauss's law. A good Gaussian surface is a square box that surrounds one of the plates. Just put it on the bottom plate snugly. The field only goes through the top of the Gaussian surface. There's no field that penetrates the bottom Gaussian surface. So Gauss's law, E dot A is 4 pi kq enclosed. Field's penetrating at a right angle on the top surface. We know what the field is, 10,400 newtons every coulomb. There's the area of the top plate alone. 20 centimeters by 20 centimeters, which is 0.2 meters by 0.2 meters. It's a square. The area is the length of one of the sides squared. I put in the constant. The only thing we don't know is the charge enclosed. We can solve for it. 3.7 times 10 to the minus 9th coulombs. And our Gaussian surface has the whole plate. So the magnitude of the charge separated by the plates is 3.7 nanocoulombs. This means there's plus 3.7 nanocoulombs on one side, minus 3.7 nanocoulombs on the other side. That's problem 3.